Hello and welcome to Convergence. My name's Mike Doran. I'm a California attorney. Albert Einstein said among the most difficult problems in all of physics is Earth's magnetic field. I believe it's the most difficult problem in all of biology. Convergence is this idea that technologies in different areas are advancing rapidly, and then at some point one area connects with another. Specifically, I'm going to talk about physics and biology. Today, I'm asking the question, why is there a lull in California earthquakes? There's an article that published on April 5, 2019 by Stephanie Pappas. It's entitled From Live Science, California's Eerie Earthquake Pause is Unprecedented. Now, Live Science is basically reporting on a paper, that scientific paper. It's not the paper itself. This is a reporter who reports on a paper. The article starts out, "It's a little too quiet in California, seismically speaking. The state is experiencing a century-long lull, ground-rupturing earthquakes, tremblers that actually offset the Earth at the surface. The 7.9 magnitude Great San Francisco earthquake of 1906 was ground-rupturing quake. Photographs taken in its aftermath show roads and fences with new bends and twists. Now, new research finds that this 100-year earthquake gap is very unlikely to be a statistical fluke. Instead, something geological is causing the peaceful period. We're unusually quiet," said, again, this is in her paper, said study co-author Glenn Basie, a geophysicist at the U.S. Geological Survey in Pasadena, California. "The biggest faults and the faults carrying the most slip have not ponied up." Slip refers to the movement of strike-slip faults, which are prone to produce ground ruptures if they're large enough. That's because slip faults feature two chunks of crust moving alongside each other in opposite directions, like trains passing each other on a set of north-south tracks. After a slip strike quake, the surface can be shifted. The center line of the highway, for example, would stop abruptly and pick up again a foot to the left. In the 1914 conference in Alaska, David Jackson, a professor emeritus at the University of California, Berkeley, noted that the Golden State hadn't seen one of those quakes since 1918. The century-long gap looked improbable when compared to previous quake patterns in the state. In his talk, memorably titled, "Did Someone Forget to Pay the Earthquake Bill?" Jackson wondered if something was wrong with the scientists' data on historical earthquakes. That's where Basie and co-author U.S. paleoseismologist Catherine Shearer came in. The two are experts on long-term earthquakes and knew they could figure out, whether the seemingly weird gap was just a fluke in the data. The pair analyzed seismic records going back 1,000 years from 12 sites on 5 branches of California's major fault system: the Northern Andreas Fault, the Hayward Fault, the Southern Andreas Fault, the San Jacinto Fault, and the southernmost San Andreas Fault. The system spans from well north of San Francisco all the way to the border of Mexico. By comparing time gaps in the ground rupturing activity at all the faults in two different data sets, the researchers found that the likelihood of all 5 branches quieting down for a century all at once, just by chance, was slim to none. In fact, the researchers put the likelihood at 0.3%, that a quiet period, just a quirk of statistics. So what I want to talk about is, again, from the prior episode, methane hydrates. Methanogens, again, are some of the oldest life on Earth. And one of the incredible things about them is genetic research has advanced, is it's being learned that not only have methanogens not become complex life like us, they've evolved basically not to evolve. They've dropped some things to become very simple. But one area where they have involved complexity, and it's the only area, is their metabolic complexity that they've gotten so that they can take carbon dioxide and water and produce methane very efficiently. So whatever its function is, there's incredible selective pressure on them to not evolve, to not change from what they do, except for to do it better. As I explained in the last episode, methane hydrates are a form of ice that form under 1,500 meters of water under cold oceans and cold temperatures. Typically, they line the oceans like a ring in a bathtub, and they're close to river systems. They're highly sensitive to what the rivers are doing. So the rivers will, let me back up. So the methane hydrates are more buoyant than the ocean that they're in. The only way that they stay fixed and down at those depths and remain frozen, basically a methane molecule, which is CH4, surrounded by water molecules and frozen in a solid form. The only way that they can remain down there at depths is if they're weighed down by sediments. So they're very sensitive to what rivers are doing. And the other thing that is interesting is methane hydrates are part of plate tectonics and part of mountain building. So what you're going to have is you're going to have continental plate like this, and then you're going to have oceanic plate like this, and you're going to have rivers flowing sediment and so forth into this area here, and then as plate tectonics works down, the methane hydrates will get pulled down underneath, and then often that process is part of mountain building and volcanoes, and California certainly has volcanoes and mountains, and one interesting thing that's also recently been discovered is this process of water eventually moving underneath the continental plate, but by way of methane hydrates, is a source of conductivity underneath the continental plate, because that water mixes with minerals and other things and just basically becomes conductive brine or salt water. And a big time source of conductivity, where you're going to have a conductive pathway between the salt water of the ocean and then up the volcanic vents and so forth, where it itself is heated rock, which is also conductive. You end up having a conductive pathway that gets you up a mountain and then close to the heavens, where again you have a lot of the higher you get up, the closer you're going to be to clouds. The clouds themselves are going to follow pathways up, rising up the mountain, and you're going to get cooling and instabilities and thunderstorms in the mountains. So what's going on that's causing the lull? Well, we've built dams up and down the coast, up and down basically that part of the Ring of the Fire from Alaska all the way down to Mexico now. This massive dams, starting at the turn of the century, increases in logging, increases in all kinds of disruptions in the rivers along California and along, in particular, but also along the Pacific Northwest, and then south to Mexico, where 3 Massive dams recently have been built on the Rio Grande de Santiago. And all these things, particularly in the Gulf of California, affect methane hydrates and their stability. So what's the danger here? Well, the danger is that all these tectonic processes, and we know this by the fact that there's so much selective pressure on the methane or the methanogens that they aren't more complex. There's selective pressures for them to be the way they are. And if we're taking the methanogens and the methane hydrates out of the equation, we're going contrary to what their biological purpose on a living Earth is. And this goes again to how a living Earth has kept the Earth's magnetic field dampened and within a range that it functions. If the Earth's magnetic field gets too strong, it's going to attract too much atmosphere, too much dust, too much gases from space. If it's not strong enough, it gets stripped away just like Mars, and we have a dead planet. So it's just at the right level because that's what life, over time, the selective pressure on these processes, these large-scale processes, even though we're talking about very tiny things and tiny microphysics and electrical currents, and the electrical currents part of it has to do with how the subterranean is heated, and so there's definitely a snowball effect by what is going on with the rivers, particularly the dams. The dams create a defect because it delays when the flow comes. You get flow during the dry season. The nearshore biosphere reads that as snow in the mountains and feeds back heat. The methane hydrates, when they're released, it's about carbonation because the methane is consumed by bacteria that fairly quickly turns it into carbonation. And the methane hydrates are very sensitive to what's going on with the rivers. And our rivers now are very much subject to these dams. And then nearby, in the Gulf of Mexico, where there is not a drought, you're getting these phytoplankton blooms, largely owing to a dead zone created by fossil fertilizers. So there's a compounding of the problem because while there's a lot of farming, of course, in California, it doesn't match the farming in the rest of the country from the east to the Great Plains, where there's a tremendous amount of farming, tremendous amount of fertilizing, and a tremendous amount of flow down the Mississippi, a little to some extent the Rio, but certainly other rivers that flow into the Gulf of Mexico. And that's where that dead zone is. You can see it with your own eyes. It's on several websites. It's huge right now, and consequently, there's a tremendous amount there's a normal amount of rainfall from basically the Rockies going east. But here the reservoirs are drying up, and it's not a drought per se, even though we have a period of high cosmic rays that affect blocking features. It's something clearly more permanent, and there's no more evidence of this than the lack of seismic activity in California, because this is telling you that the very feedback processes related to methane hydrates are damaged to the point where the seismic part, the mountain building and the volcano building and the earthquake building, the earth movement, plate tectonics is being shut down. Okay, thank you for watching. Please hit the like button and subscribe. This is a serious issue. It's not being discussed. CO2 is not interesting as a greenhouse gas. It's interesting in clouds in the context of low frequency electromagnetic fields. It's about a living Earth. It's about life dampening the Earth's magnetic field to keep it in a functioning range. We have to learn how to be stewards and live within this. Thank you.